Hello and welcome to the CompTIA Cybersecurity Analyst CISA Plus Certification Study Guide. In this video, we will discuss Chapter 4.3, More Network Indicators. Please like, subscribe, and hit the notification bell. Steal data. Attacks that are designed to steal data will communicate with the CNC server as the means to transport the data back to the threat actors. A variety of techniques can be used, and it often depends on the cunning and ingenuity of the threat actors. This can be illustrated by the infamous attack on the point-of-sale (POS) terminals at Target Corporation that lasted only 3 weeks but resulted in over 40 million credit and debit cards stolen along with 70 million records of personally identifiable information (PII), including the name, address, email address, and phone number of target customers. As credit and debit card data was captured whenever a customer swiped their card at a POS terminal, the card numbers were encrypted and uploaded back to the Target network to be deposited on Target internal servers that were under the control of the threat actors, who had also installed backdoors on 3 Target FTP file transfer protocol servers. These backdoors were created using carefully chosen usernames to blend in with network management software. At set intervals, the stolen information was sent to the closest Target FTP server and then transferred to CNC servers in Miami and Brazil. The impact of the attack on Target was substantial. Not only was the Target CEO forced to resign due to the incident, but Target registered a 46% decline in profits compared to the prior year, much of it attributed to consumer backlash at the attack. Target was also forced to spend over $100 million upgrading its POS devices. Threat actors use different techniques to hide their stealth transmissions so they are harder to detect. One technique is to use standard network protocols that do not attract attention. For example, when sending stolen data, the malware may use the HTTP protocol, which can easily blend into normal traffic. However, the volume of traffic may make the beaconing detectable. HTTP traffic generally has more volume incoming from external sources than outgoing, so that threat actors exporting large amounts of stolen data could be identified. In the Target attack, stolen data was only sent internally to the Target FTP servers during peak times of the day in order to hide evidence of communications. And because FTP was a common protocol used by Target, this did not raise suspicion. A more advanced technique to mask both types of stealth transmissions, irregular peer-to-peer communications and data exfiltration through beaconing, is to combine standard protocols with an internal mesh network of infected devices so that the devices can communicate between each other easily. This allows for a single compromised endpoint to act as an internal CNC device. This one device receives instructions from the threat actor's main CNC server and then distributes these commands to other compromised endpoints, while also acting as the single exit point for sending stolen data back to the threat actor's main external CNC server. This is called a peer-to-peer command and control (P2PCNC) configuration and is illustrated in Figure 4.6. A P2PCNC configuration has several advantages for a threat actor: reduced number of external beacons. A P2PCNC has only one single device that performs beaconing with the CNC server instead of each device. This results in less traffic beyond the edge of the network that likely would not raise suspicion. Aligns with traffic inspection prioritizations. Most security technicians tend to maximize the priority of inspecting external traffic on the edge of the network while minimizing inspection on the internal network. The assumption is that there is more risk from external traffic than internal traffic. Because a P2PCNC has only one device communicating externally, it better aligns with this tendency. Does not use restricted protocols. Most networks treat certain classes of traffic differently, depending on if it is used internally within the network or at the edge of the network for external communications. A P2PCNC does not have to rely on restricted protocols that draw attention. One means of how a P2PCNC can circumvent restricted protocols can be illustrated in the following example. HTTP traffic, port 80, is routinely allowed as outbound over the edge of the network so that employees may browse the internet. However, HTTP traffic is restricted if it originates from internal servers or a high-value network subnet. a standard CNC approach that requires each infected device to maintain contact with restricted servers or high-value subnets using restricted protocols like HTTP will raise red flags. In a P2P CNC configuration, external beaconing typically uses HTTP because this protocol is so common. For an internal network that uses Microsoft Windows devices, a common protocol widely used is Server Message Block, SMB. A named pipe is a logical connection, like a TCP session, between a client and server that uses SMB. The name of the pipe serves as the endpoint for communication in the same way that a port number serves as the endpoint for TCP sessions. Thus, named pipes, a native Windows technology that allows for inter-process communication across remote systems over the SMB access protocol, can be used for internal P2P CNC communication. This allows for the internal devices to communicate through the mesh network using common protocols without raising any alarms. SMB is not the only protocol that can be used internally for P2P CNC. Essentially, any protocol that supports reading and writing data between two devices could be used. Other inter-process communication options on a Windows network include Windows Management Instrumentation, WMI, Windows Mail Slots, and even Active Directory, AD. It is generally recognized that detecting P2P CNC can be difficult since the traffic uses standard protocols to blend in with normal internal and external network traffic. However, some symptoms can be helpful in detecting a P2P CNC. These include abnormal processes to named pipes. After collecting and creating a baseline process to named pipe relationships, security professionals can watch for new events compared to the baseline. Known malicious named pipe names. If the threat actor does not change the default name of the named pipes that now generate large amounts of traffic, this could be a symptom of a cyber incident. Abnormal named pipe security descriptors. P2P CNC often applies a single security descriptor to a named pipe that allows full control to an everyone group. Monitoring named pipe security descriptors can also be a symptom. When examining networks for stealth transmissions, the following may serve as symptoms. Remote connections to named pipes. Using a network tap or collector, SMB network traffic can be inspected to look for a remote connection to named pipes. Abnormal host-to-host traffic. If certain high-value servers rarely, if ever, create network connections with certain network subnets that contain user workstations, but suddenly a high number of network connections is identified from one of these high-value servers to a workstation subnet, this could be identified as abnormal. Detection of a P2P CNC is considered difficult because it uses normal protocols and features. Generally speaking, it may be easier to detect malicious behaviors of the infected device itself. In preparation for unleashing a cyber incident, threat actors will perform scans/sweeps on a network to uncover any vulnerabilities. These scans/sweeps include ping sweeps, determining if a device is awake, and port scans, looking for available services on open ports. Any scans/sweeps originating from unknown IP addresses should serve as a potential IOA that should be investigated. A final symptom of an IOA is unauthorized devices on a network, called rogue devices on a network. On a wired network, a rogue device may attempt to monitor network traffic. For example, a managed switch on an Ethernet network that supports port mirroring allows the network administrator to configure the switch to copy traffic that occurs on some or all ports to a designated monitoring port on the switch. A threat actor, or more likely an insider who is performing work for the threat actor, can connect a rogue monitoring computer to the mirror port and then view all network traffic moving through the switch. The monitoring computer can be a standalone device or a computer that runs protocol analyzer software. On a wireless network, a rogue mobile device can connect to a weakly protected wireless network. These are particularly dangerous since they can provide unfettered access to the entire network, bypassing network security protections or tricking users into connecting with a sinister AP. Several methods can be used to detect a rogue AP by continuously monitoring the radio frequency, RF, airspace. This requires a special sensor called a wireless probe, a device that can monitor the airwaves for traffic. There are 4 types of wireless probes. Wireless device probe. A standard wireless device, such as a portable laptop computer, can be configured to act as a wireless probe. At regular intervals during the normal course of operation, The device can scan and record wireless signals within its range and report this information to a centralized database. This scanning is performed when the device is idle and not receiving any transmissions. When a large number of mobile devices are used as wireless device probes, it can provide a high degree of accuracy in identifying rogue access points. Desktop probe. Instead of using a mobile wireless device as a probe, a desktop probe utilizes a standard desktop computer. A universal serial bus, USB wireless adapter, is plugged into the desktop computer to monitor the RF frequency in the area for transmissions. Access point probe. Some AP vendors have included in their APs the functionality of detecting neighboring APs, friendly as well as rogue. However, this approach is not widely used. The range for a single AP to recognize other APs is limited because APs are typically located so that their signals overlap only in such a way as to provide roaming to wireless users. Dedicated probe. A dedicated probe is designed to exclusively monitor the RF frequency for transmissions. Unlike access point probes that serve as both an AP and a probe, dedicated probes only monitor the airwaves. Dedicated probes look very similar to standard access points. Once a suspicious wireless signal is detected by a wireless probe, the information is sent to a centralized database where wireless LAN, WLAN management system software compares it to a list of approved APs. Any device not on the list is considered a rogue AP. The WLAN management system can instruct the switch to disable the port to which the rogue AP is connected, thus severing its connection to the wired network. Any unknown network device that is discovered connected to the network should be treated as an unauthorized device and immediately disconnected from the network. Further investigation should reveal if the device is being used by threat actors or is the result of a faulty change control process. If you find this video useful, please hit the like button, leave a comment, and subscribe to the channel. To see more videos like this, please click in the rectangle in the middle of your screen. To see other videos from this channel, please click the circle on the bottom right. Thanks for watching. We will see you on the next one.